Um,
All right, so thanks Yunfei and Brandon for coming. I know this is the day before long weekend, so once in a while you will have to say that, well, I think at least we have two of you, and it's better than having no one here. Yeah, and okay, so today we are going to talk about our last lab. It's about parallelism. Although it's the last lab, it's probably very important because as you are already aware that parallelism is everywhere in our life, in the world of computation. So in fact, in this class, we have covered instruction level parallelism, pretty much talking about the ability in your processor to exploit the concurrent execution of instructions. So that's instruction level parallelism. And today in the lecture, we talk about thread level parallelism in a way that we are able to run two instances of programs at the same time. And to cover the fact that there is limited instruction level parallelism in your code in a single program. And today we are also in the lab, which is the part that we haven't talked about in the class. And unfortunately, because it's 142, so we don't actually have a lot of time and resource to talk about that. But another kind of parallelism is actually more important nowadays because of the population of machine learning and in general, vector and matrix operations. That's called data level parallelism. So right now, nowadays, when people talk about parallelism, there are these three different types of parallelism. And regarding data level parallelism, it means that if you think about vector operations, you are basically perform pairwise operations concurrently for everyone in a vector at the same time, right? So that's vector level parallelism, or say data level parallelism. So and there's another taxonomy of parallelism that you might already learned in your textbook. That's actually the SIMD, SISD. Well, that's actually SISD, SIMD, and MIMD. So SISD is actually saying that there's no parallelism and it's single instruction stream, single data. So when you are using your processor to execute instructions, it's pretty much the case, right? When you are exploring your ILP, that's pretty much the case. You have multiple instructions and each instruction is working on their own data, and that's SISD. And the second type of parallelism that people would talk about execution model is called SIMD. It means single instruction stream, multiple data. So by single instruction stream, it means that I only have one instruction that I'm currently running. However, that instruction has the ability to operate on multiple pairs of data, right? So if you hear that multiple pairs of data concurrently, wasn't that something similar to vector operations? So in fact, SIMD is pretty much resembling the data level parallelism that we were talking about. And another type of parallel model is called MIMD, multiple instruction streams and multiple data. So by multiple instruction streams, it could be like different threads, different programs, right? And multiple data, like each of them is working on different parts of your program or your program input, right? So pretty much thread level parallelism is belonging to the type of MIMD models. So, people like to use different jargons to talk about the same thing. So that's why I want to bring this up, because you might see SISD, SIMD, and MIMD a lot. However, if you think about the processing model behind it, they are actually talking about those processing model that we have been talking about. So you might be familiar with this graph already. It's essentially the same pipeline diagram that of the processor that we have been using in your lab across, starting from your very first lab to now. So you should be very familiar with it. And for this one, right, you can see, well, this processor has the ability to run up to 12 instructions at the same time. So this is an example that modern processor has the capability of exploiting instruction level parallelism. And in the last lab, we have been doing a lot in telling you how to exploit the instruction level parallelism. And today in the lecture, we talk about modern processors. In addition to instruction level parallelism, we also have thread level parallelism in a way that you can either use simultaneous multi-threading by having each processor present as two front-end instruction front-end, so that the operating system can fit you with two streams of instructions and each of them running on different data, right? So that's kind of like the MIMD already. However, on top of that, each core can be duplicated so that you have multiple cores that are concurrent, that can execute stuff concurrently in your program. So that's actually what we can exploit in thread level parallelism, is that nowadays your processor not only have SMT but also have CMP, right? So that's an example of how the hardware can exploit the thread level parallelism. And you might ask, where is my data level parallelism? And in fact, if you look carefully, pay attention to your processor core, there is a region called vector processing units. So with the vector processing unit, you can see there is a FMA 512. It means that the FMA unit can work on 512 bits of data at the same time. So if you think about 512 bits, it's actually 8 numbers, right? So it means that I'm able to perform 8 numbers multiplication and accumulation. So this is pretty much will give you a vector inner product, right? So that's FMA 512. You can also have FMA, right? And floating point multiplication and accumulation, right? So, and you can also have an ALU, the vector ALU that this ALU, like you have these 3 ALUs, they can work on different pairs of data. And you might, okay, so this is something new. And not a lot of people know this because its availability is also only limited to server products in Elder Lake. So if you have a, Intel Sapphire Rapid processor in your virtual machine instances, for example, if you are now using Google Cloud, you might be able to create an instance that is based on Sapphire Rapid processors. Then you will be able to find AMX extensions in your instruction set architecture. And the M here is actually matrix. So what does that mean? Is that this AMX would allow you to input a matrix, well, 2 matrix tiles, and they will give you the output of another matrix tile. So you can imagine with this AMX instruction, I can actually do matrix multiplications more efficiently than what we have been knowing so far. However, because this AMX instructions, they are only now available in Sapphire Rapids processor, which are the server version of the Elder Lake architecture. So unfortunately, I'm not that resourceful to give you a few nodes with AMX. So that's why in your architecture, that although we are using Elder Lake, however, we are not going to see AMX in your processors. But with this vector operations, vector units, your processor has the ability of exploiting data level parallelism, which means that a single instruction will work on multiple pairs of data. So another place you will see a lot of data level parallelism is actually your GPU. So if you check the NVIDIA GPU architecture, it's pretty much like this. So nowadays, there are tons of stuff that I can talk about GPU because that's also my research is about. But unfortunately, I'm only allocated for 5 weeks, and next week I only have 2 lectures. I won't be able to talk about that too much. But modern GPU is pretty much like this. So each of the gray area is a string multiprocessor. So when we say string multiprocessor, you can think about that. You are getting a stream of data, and by stream of data, you can imagine that they are typically vectors. And what are we going to do with the streams of data is that you can use a vector of an array of ALUs, and each of them will work on the same thing. So for example, this 14.32-bit unit, right? If I want to activate them, they can all do the same operation because they have only one control in this SM. So what does that mean is that, okay, for example, here I have how many? I have 16. I have 16 14.32 units. It seems like I can perform 16 floating-point operations at the same time. However, a restriction here is that this 16 floating-point operations, they have to be the same. They have to be 16 add, 16 multiplication, 16 divide. So in this way, you can imagine the usage of the best use of them is having them perform vector addition, vector multiplication, vector subtraction, vector something, right? Everything vector, right? So this is, but if you think about that, right, it's also fulfilling the programming model of single instruction string, multiple data. So that's GPU. So a lot of people were thinking about, so one thing I hate about NVIDIA is that they try to advertise their hardware as a multi-threaded hardware. It's not totally correct because by thread, we are thinking that each thread can have its own freedom. Each thread has its own individual control flow. However, in NVIDIA's definition, each thread can only be run with the same control flow, with the same set of operations. So you won't be able to deal with any loop iteration that has an if-else statement there. So that's the big limitation of GPUs. So, but in terms of the workload that we have nowadays on GPU, right, that works pretty well. So that's why a lot of cases, we still see GPU as a very important computation unit. So here we summarize the parallel models that each different hardware in our modern computers will support. So we'll give you some idea about like, okay, when people talk about parallel hardware, what's their limitation and what's their ability. So again, those parallelism doesn't come for free. If you don't say that you can parallelize it, no one can actually parallelize it, right? And even for instruction level parallelism, the hardware has done a lot, right? And in many cases, if the compiler doesn't do anything, if you're as a programmer, you don't do anything, there's limited amount of parallelism that we can tell automatically. And this is even worse for thread. If you don't say that I want to generate a thread, there's no thread level parallelism to be generated. So it's very important for us to know how to create a thread. So this is the abstracted multi-threaded machine, which I also show in a lecture today, is that our software system or programming model thought your hardware has individual cores, no matter it's SMT or CMP, and they can share their memory. That's what we thought. But we also know that we have caches, and let's assume the hardware can address that, right? Then how are we going to program? How are we going to create threads running on top of it? And there is a library that it has been adopted by most of the operating system nowadays called POSIX threads. And if you hear pthread, that's pretty much it. And in pthread, there are several basic elements there, which in this lab, I'm not going to let you touch it, and we are going to give you a very good abstraction. But as an educator, I want to let you know how the backend was implemented. So on the backend, there are several elements there. So each thread is pretty much like a file, because if you think about, I don't know how familiar are you guys with Unix, but by default, everything in Unix is a file. So a thread is also a file. And in fact, when you create a file, when you create a thread, there will be a file created in a file system of your Linux associated with it, which is hard to believe that, but there is a directory called proc/proc in your Linux or Unix system, and every process would have a file under /proc. Every hardware like CPU, GPU, or whatever hardware that you can imagine, they also have a file in /proc or /dev. So everything is basically mapped to a file in Unix or any kind of system. Because, well, some of you might argue that, well, I'm using Windows, how come I should care about it? I'm using Mac, how come I should care about it? In fact, in Mac is also based on BSD, a distribution of Unix system. And Windows, it used to be Microsoft has their own kernels, but after Windows 2000, everything becomes Mach based, and Mach is also another distribution of Unix. So, well, another descendant of Unix. So everything is pretty, and Unix file is the universal abstraction. So every other operating system also leverages that abstraction, and because it works very well. And if everything works well, why should we change it? And so the descriptor here is pretty much saying that I'm going to create a file or create an identity called a thread. And so when you declare that, you will use pthread init, right? So pretty much like create a file. And then when you want to start running a thread, you use this function called pthread create. So this pthread create, it will require you to give a function pointer. First of all, let me see. Okay, you have to give it a thread descriptor and match it with a function pointer. And regarding function pointer, we briefly describe it in a lecture. Like it's basically a memory object and it can be pointed to any function. So here, if you declare a function that I want to run as a thread, here's the place that you have that function. But again, it has some kind of restriction on the type of function pointer. So you have to make sure that when you declare a thread function, you have to be able to cast it to the function pointer format. And there are some attributes about when I create a thread, is there any restriction on the thread? And some arguments, because this is essentially a function and you want to pass arguments into this function. And that's where you can pass this argument so that when you launch the thread, the thread function would be able to run with the arguments that you want. So if you look at this function interface, you will figure out the thread idea is basically I run a function in a system with the argument I want on a separate hardware unit, potentially. So every thread is basically an instance, an invocation of a function on a different hardware. So that's what the thread is basically doing. And when you are done, there is a function called pthread join, which is the synchronization point of all function, which means if I want, so P-thread join means that, okay, so in the meantime, you might spawn a lot of threads at the same time, but P-thread join means that every thread that I spawn needs to, I want everyone that I specified that has been spawned to finish before I can proceed. That's called synchronization. So it's pretty much like, okay, I'll allow you to go any, well, so, okay, I don't know if that's like, okay, in a tour, right, in a trip, right, a lot of you might be divided into small group, you want to have your own schedule on things, but the tour guide or the leader would say, okay, at 9 o'clock, I want to see everyone here, right, and we won't move until everyone shows up. So this is pretty much like a thread join, right? So every thread can do whatever it wants. However, at the join point, the program won't be able to make any progress until every outstanding thread has been finished. So that's thread join. And there are also locks that we can talk about. So this is, but in your lab, here's the abstraction you will see. You will see, first of all, we will include thread. That's a header file we have. And within that thread head file, you will be able to create thread easily through standard library thread and just declare like T1, T2, T3, right? So T1, T2, T3, there will be the thread descriptor that we created for you. And the goal will be the function that I want each thread to execute. So this is essentially the thread function. And as you can see, it's a void function. But if you have a return value, you have to cast it here. So that's pretty much how you create a thread. And we also call the join function, which means that, okay, if T1 didn't finish, we cannot make progress. If T2 didn't finish, we cannot make progress. If T3 didn't finish, we cannot make progress, right? And if you have many threads, you probably can also make this thread as an array and join in the array fashion. So, but in this way, you can see the C++ abstraction we provided in the lab is a lot simpler than using pthread create. And okay, so I don't know how many of you have seen this before, but in your operating system, there's a notorious or no famous buffer problem, right? So it typically saying that, okay, I have a producer. You can imagine the producer as a thread. I have a consumer. You can also imagine a consumer as another thread. And the producer keep inserting new values into the queue. And the consumer keep looking over the value that we have in a buffer. So once we are done, once we look over the value, we remove a value from the buffer. So that's the implementation. So you can naively write a function like this. So for example, I can have a thread that keep inserting value and outputting value. Draining value from the queue. Right. This will be two threads. However, right. Most of the time we have a very I would say wrong expectation about how our hardware execute this thread. You might think, oh, this is the main thread, it must go first. You think this is the spawn thread, it must go later. And then everyone works on the same pace. So I never have to worry about the case that the producer is slower than the consumer. However, in your operating systems, there will be context switch. So your consumer may be switched out at some point. In your operating system, there's power saving. So we might slow down one of the processor core. In your processor, there will be, when you are running your program, you may interface cache miss, which make both of them slow down, right? And when you resume, there's no guarantee who is going to start first, right? So there are too many things that would make this program getting wrong. So what really important is that we have to maintain something called a lock. So this is called a lock critical section. So only one of them can enter this section of code. So I know like, so then I can maintain this in and out values properly, right? Sorry, I can, yeah, I can maintain this in and out value correctly, so I can check if I'm going over or not, right? So that's why you need a critical section. However, I don't know if you have learned this in operating system class. You did? Okay, implementing such a lock is actually more complicated than you can ever imagine. So for example, their context switch, it's a lot of you saying that I can use a spin lock, which means that I keep checking a variable called spin. However, what if context switch occurs when you are checking, right? Or what if, when you are checking and when you are modifying, right?
What is the volatile keyword?
Okay, you will learn it in the next lecture, but it actually means that we force the variable has to be in memory, right? So, and also, what if the thread crash, right? Then your lock will be gone, right? So, or, right, like if all thread can see lock at 0 at this point, maybe more than one, and modifying the lock at the same time, right? Because for this pieces of code, it only checks if the value is 1 or not, right? So more than one can go into the critical section in this case. So this is not a very good implementation, right? So in your processor nowadays, we have to support an atomic instruction like lock and exchange, which would lock a cache line that the share variable or say the lock belongs to. So only one of the processor would be able to get the access to the lock and then modify the value. And this lock, and with that operation, right? So what would happen is that you would use this sequence of assembly language which lock the cache line and compare and swap the result. So by compare and swap is an instruction that check if the current value is the value that I want. If that's the case, I swap the value with another value. So pretty much like if I find the lock value is 0, then I swap it to be 1. And because you lock it, only one of them can successfully change that value. And because this is a single instruction, so it's an atomic unit of operation, so you will avoid a case that multiple of them would interrupt in the middle. So that's why your processor needs a lot of support for that. You might think this is an easy thing to do. However, in your Q3 to Q4 and Q8 to Q10, we will show you that locks are very expensive. And you will generate a lot of figures like this. And this is the execution time of an example that when we apply locks in our code. And as you can see, the execution time, this is the baseline. This is the baseline. One thread, no lock. Then one thread, no lock takes only like this amount of time to execute. But once you added a lock, right, simply the locking overhead itself takes about 0.86. Because you think about the operation you need to do, right? You need to lock the cache line, you need to execute an atomic instruction. And when you execute that instruction, the IOP is pretty much just 1 because you are the only one instruction that can be in place, right? So the performance is really bad and you are sacrificing the instruction level parallelism to fulfill your demand of atomic operation. And if you have multiple threads, because everyone has to do the same and everyone has to wake another, and we have coherence protocol and consistency protocol running at the end, right? So if you have 2 threads, the performance is actually terrible, right? Like it's 3.6 seconds, way slower than without threads, right? Which tells you that, okay, if you have the thread is the thread lock is a very expensive thing to do, right? So although we think, well, parallelize the program would be helpful, but locks is actually a big problem. And later on, next week, you will learn that, well, we kind of like talk about today. regarding the coherent stuff, right? Because we want to make sure that everyone sees sum as deadbeat. So to maintain this is actually very expensive. And the other thing is that to implement that, and remember, the cache is managed by blocks. And each blocks would contain multiple variables, not just the one that you are invalidating. So it turns out that you will create a lot of unnecessary cache misses, even though you are not really sharing the data. And that's called false sharing problem. And that would be an issue that you have to deal with when you are performing multi-core operation, more multi-threaded programming. So one example that you will see in the lecture next week is actually, wait, why am I going to so fast? Okay, so one example you will see is that, okay, if you coded your code, if you write your code in an interleaving way and a chunking way, the access pattern of your data is pretty much like this. A lot of you might think a fine-grained partition shouldn't make too much difference with a coarse-grained partition, but turns out because the fine-grained partition, this would consider to be like a cache line, right? And if they are running on different processors, you can imagine one would invalidate another. So your cache miss rate would be terrible in this case. So there are lots of stuff you have to play with carefully when you are doing programming on threads. So for example, you have to reduce sharing. Better, there's no data dependency, there's no data sharing among them. Even though you have sharing, make sure that they are read-only. That would be the best practice for thread programming. And if you really have to update data, right? Sometimes you need lock, but avoid fine-grained locks in a way that, okay, if I have a lock that is only locking a tiny pieces of a code, and this tiny pieces of a code is executed frequently, and if it's unnecessary, don't do it, right? Because think about the nature of locks. You're pretty much forcing only one thread can enter that critical section. So if you have, once you have a lock, you are pretty much serialized the execution of all threads. And so then your performance is pretty much like a single threaded, and even worse at that time.
So kind of related to that, in the example where we have like thread 1, thread 2, thread 3, and then we join them one after each other, is that serial basically because they're waiting for each other? Or
no, at that time, right? So the join is only checking if T1 is done, T2 is done, T3 is done. But when I check, of course, the main thread is waiting for T1 to be done. But in the meantime, it doesn't prevent T2 to make progress. So if T1 is done, but in the meantime, T2 is done, this is just like shoot, right? Okay.
And sorry, also, so I think you mentioned that there's, so we run main with T1, T2, T3. Technically, there is a main thread as well, right?
Right. So there are 4 threads, to be honest. Yeah. Okay. So also, right, because each thread, when you set them up, right, you have a thread spawning overhead. And when you join, right, you also have an overhead. And when you destroy them, there's also an overhead, right? So if you want to make your thread programming efficient, there's another programming technique called thread pool. What we would typically do is that we have a thread that is keep running there. We just change the function that the thread is running so that we don't have to suffer from the thread spawning overhead. But in this lab, we didn't test that because I think it's too much for us at this point. But another thing that you want to know is that, okay, if I want to write a thread, that thread needs to be performing sufficient amount of stuff rather than just one thing, right? So that's the thread. So we know that we have simultaneous multi-threading. We know modern processors have those. But one thing, right? You also have to be aware. If your processor right now, we know some of them are physical cores, some of them are virtual, or say fake core IDs, which means that, okay, like this case, right? I have the pages and Slack. They all map to the same physical core. And as we go through the questions in a lecture today, right? You know, there may be some issues with sharing resource within the same physical cores. So you can imagine these 2 threads, they might not be able to get what they want as an individual cores, as they are running on individual cores. And in fact, right? If you are using an SMT processor in one of your lab example, you're going to see this graph. So if I have 4 threads, then the processor pretty much make a pretty good, the operating system make a pretty good mapping that each of them would be operating on a separate core. However, if I have 5 threads, then the 5th one has to share with the first one. So it turns out you see the speed up get get slowed down, right? Because it means that that's actually the effect of competition in your hardware resource. And when you have 6, it's going better, but it's never going to be better than the case we only have 4 threads. So a lot of us has the wrong expectation saying that if I have more threads, I should be able to get better performance. But sometimes yes, sometimes not. It depends on your hardware capability. So if you oversubscribe your hardware with more threads, like this case, right? If you look at the case, we have 8 threads. It's actually not even better than you. It's probably pretty much like the case when you have 3 threads, right? So 8 threads is not necessarily better, right? And if you have 7 threads, it's even worse than the case when you have 3 threads. So be careful. And sometimes if you don't know how many threads your hardware supports, but naively increase the amount of threads we have, then you are going to hurt your performance. And so talking about data level parallelism, so that's the part of stuff that we probably would not talk a lot in the lectures. So when we talk about data level parallelism, it's pretty much referring to the execution model called SIMD, single instruction, multiple data. And so it's pretty much like, okay, single instruction stream. So for example, I have 2 vectors. So they are multiple pairs of data. And single instruction stream, because if I want to perform vector sum, that sum addition is the single instruction that I want to apply on this set of pairs of numbers. So turns out you can do the same thing at the same time. And SIMD is a very frequently seen instruction extensions in modern processors. For example, in x86, they have SSE, and later on they have AVX, advanced vector extensions, or previously it's called NNX. So they have several different versions of vector instructions, and it's too complicated in a way that I cannot even tell what their differences are nowadays. But you can imagine all of them are SIMD instructions. And ARM also noticed that it's important for them to support that. So ARM has an instruction set extension called Neon. It's also for vector instructions. So to support vector instruction, you are pretty much having a hardware pretty much like this. You have a set of vector registers, because all you want is the ability that I can operate on a set of numbers at the same time. So when your hardware deal, so your instruction is pretty much like I have a single instruction like add, and this add should be applied on this vector registers and this vector registers, and put the result to another vector register or the same vector register. That's pretty much the format. So and on the hardware side, all you need is a set of LUs that shares the same control. And when you are running this instruction, just map these pairs of input to corresponding LUs and then store the result to the target vector registers. So that's pretty much how we implement the SIMD hardware. So, and it has a lot of extensions. And nowadays, as I said, if you check your code, right, like in Intel processor, we pretty much has XMM registers, which you might already seen a lot when you are digging into the assembly code. And so there are a lot of SSE extensions, and you can use the register to store multiple double precision or single precision numbers, right? So for NVIDIA processors, as NVIDIA GPUs, as we said previously, this, okay?
I was curious about this kind of architecture, and I noticed, so we have 64-bit floating kind of array, and then we have, double the amount of 32-bit, but how many operations do you actually use float data types versus doubles, or like, and can you bind those together and have like two 64 bits somehow?
Okay, so the answer is no. So that's why they have separate units there. But internally, I don't know if they have any trick dealing with that. But to the best of my knowledge, they are not. So that's why the performance of their floating point and double is pretty much pointed to the amount of these units they have. And power consumption is probably the reason. That's what I would imagine.
Like, so if I was given some kind of problem, I guess, to matrix multiply or something like that, would it probably be faster to use floats if I could do with the lack of precision?
Okay, so if you are dealing with matrix multiplication, there's something called tensor cores. Yeah. Okay. All right. So, okay. So if you want to do matrix multiplication with SIMD instructions, this is what you have to do. You have to use a lot of intrinsics, right? The first time I show you intrinsics is actually in pop count, right? But if you want to use intrinsics in matrix multiplication, right? Because let me tell you, right? You are going to do matrix multiplication again in this lab, and and if you want to do matrix multiplications, then with SSE, this is what you will have to do, right? And you will feel like, okay, now I feel like I'm programming at the assembly language level, not a high level language, right? And you have to do a lot of stuff manually. Like I have to allocate a register, vector register. I have to load the value into the vector register through this intrinsic, and I have to fill the vector register that I'm going to operate on with the matrix value that I want to compute, or the array value that I want to compute, and then add them together and store, right? So that's very, very assembly style programming. It's not like C, right? So you might feel like, okay, I'm knocked down right now, right? So in this lab, we are going to let you practice a better tool for exploiting the SIMD or even thread level parallelism. That tool is called OpenMP. So OpenMP is a C or C++ extension that has been widely supported in modern C compilers. So if you have if you have GCC, you can actually add -OMP to support in your compilation flag to enable the support for OpenMP. However, if you don't add pragmas of OpenMP in your code, there's no way the compiler is smart enough to exploit OpenMP. And the reason is because OpenMP is actually thread level parallelism, and without the programmer specifically tell the compiler where could be a thread, they are not going to generate the thread for you. So OpenMP is relatively simpler than pthread in a certain way that in pthread, you remember that even though we provide a C++ extension, you need to generate your own thread function. You need to know where should I let the thread go, where should I join the thread. And in fact, OpenMP make these things really simple with three. So basically, you only need to know 3 pragmas, and you can ace this lab. So the first pragma is called pragma OMP parallel. So okay, another thing another limitation of if OpenMP is such a great thing, why we still want the pthread or thread library is because OpenMP has its own limitation. OpenMP is only possible to parallelize iterations or inside a loop. So what OpenMP does is that if I see OpenMP parallel, I will consider the iteration in a following loop as each iteration in a following loop as a separate thread instance. So I equal to 1, I equal to 0, I equal to 2. They are all considered as an individual thread instance. And of course, because it's compiler optimization, the OpenMP itself may decide the granularity of that. However, again, right, for this, the OpenMP has no way to tell if there's dependency among your thread, among your iteration. So that's something the programmer has to tell OpenMP if it's safe to make that strong assumption. Another thing to say is that if you cannot make your thread iterations to be independent from one another, then OpenMP becomes very dangerous, because if you put a pragma in front of your iterations, then your compiler will consider it's okay to parallelize every loop. However, that may not be the case. For example, if you have a loop carry dependency, then that's going to be very dangerous, right? So that's why the compiler won't be able to do that. So, and here are a lot more restriction here. For example, because the OpenMP, they want to know specifically how many threads that I can generate. So if this is going to be modified in your loop, then this is definitely not a number that the OpenMP would feel, okay, I cannot do anything for you here, right? So again, a lot of you might think, okay, can OpenMP do nesting, right? But remember what we talked about, thread level parallelism doesn't apply to the case it's too fine-grained. So OpenMP itself doesn't do nesting itself, because they will consider, okay, coarse grain is better than fine grain, okay? So, of course, we know if we consider every iteration as independent, there will be a lot of limitation. So you are allowed to declare a critical section, a code block, or a statement that should be considered as a critical section. So the OpenMP compiler would insert join and lock or whatever that is appropriate to implement that. And there's also another pragma. So there are cases that you think having a thread is an overkill. For example, if it's only one iteration, one statement, why don't I just use SIMD, right? So you can also use SIMD by replacing the parallel or critical with SIMD, right? So the next statement will be automatically considered as a SIMD instance if that's possible. So here's how we apply the histogram, OpenMP in a histogram program that has been given in the lab. And here we only use the OpenMP to parallel the for loop, and we declare a critical section because you want to accumulate how many histogram, how many categories of how many instances belong to a histogram category. So that's what we did. And look at the right-hand side. Here's the speed up pretty well. So with this, you can imagine for this pieces of a code, we are generating a thread instances for each of the code in this between this code region. And then for this critical section, we are going to serialize the institution of critical section. Right, so that's pretty much what the OpenMP will do, and your institution of the code is pretty much like this with the OpenMP extension. And for the vector sum example, that's where we generate, where we can apply SIMD. As you can see, right, the previous example, we are going to have a coarse grain thread, which work on the three-level loop, which work on different parts of the loop, right? But here, we are going to have OpenMP SIMD work on only one statement of each, right? So that's a very good example why you should use SIMD, right? And as you can see, the generated code, it does use like XMN0, XMN1. A very good example, it tells you that, okay, we did enable SIMD in this case. All right, so programming assignment, again, matrix exponential, right? And it's continuing from the lab 2, and this time you are allowed to use OpenMP or whatever that you learn to parallelize your code. And on the gray scope, we provide 4 threads, which you are supposed to achieve 40 times speed up. And I counted I tried that on my reference solution is probably roughly around like 45 times on the nodes we have. So, but again, I can't guarantee that because depending on different implementation, different algorithm, there may be different speed up you measure on the code. But if that's the rough idea that I can give you. All right. Question?
So we're supposed to use OpenMP more of an approach rather than actually trying to like directly use threads.
Yeah, but I cannot prevent you from use threads.
But
If
you're
you,
encouraged to.
you are encouraged because it's easier.
Okay.
Right. But if you have a lot of fancy idea, you want to use intrinsics, you want to use P-thread, you think I'm a hardcore programmer and I can get everything done before next Thursday, including the time that I prepare for the CSE142 final, you're more than welcome to do that. All right. Okay, announcement before we leave. So today we are actually having the very last lab lecture because we don't have any new lab after today. Yay, right? And but you guys might think, okay, I'm just like, wasting your tuition. So as a compensation, I would have another office hour next Thursday at the same time, and I would have it 2 hours. So you got 1 more hours than than usual, right? So solve your lab questions at the very last minute, or if you want to discuss anything about CSE 142, because the next day is actually the scheduled final day, you're more than welcome to use this office hours. Other than that, thanks for your participation for today, and we are done for the lab mostly. And don't forget to turn in your lab on time. And other than that, enjoy the rest of your week. I will see you next week in a lecture, or I look forward to your lab submission.